Okay, welcome everyone to a new edition of the Field Development and Operations. So the menu for today, I thought that we left some things that you were asking questions after the previous session and some sessions before. So I think we can take some time to clarify. At least I give you some information about these sessions, about these questions that were pending, and yeah, hope to take care of them now. And finally, we close already the topic of network. How do you make calculations in network, the performance of network, and but just to use because we discussed a little bit last class about downhole networks, and there is a very important application for downhole networks, which is allocation, that I want to use also the opportunity to, I thought about doing it later, but now that we have discussed and you have already fresh to see how a downhole network looks like, that we can use also the occasion to talk about it. And yeah, so after that, so we are going to cover first some things that are you were very curious about this inflow control device, autonomous inflow control valve. So I'm just going to show you a nice video that it's on YouTube. Then we're going to talk, I'm going to discuss a bit about networks. Somebody wanted to see how a junction looked like. Okay. And then what was one more thing? Okay, we're going to have a small discussion on exercise because you already the deadline for exercise 2 is already passed, so want to make a few comments on that. Yeah, and then the topic for today, which is allocation, and we will try also to go first single phase flow, pressure drop calculations for single phase flow, incompressible single phase flow. And then after that, if we have time, I will try to reach to multi-phase flow. Because at the end, remember, we are calculating this, to calculate the performance of our production system, we need this very important, the pressure drop in conduits. And we have done all so far because it's easier for us and we can cover a lot of different things with it, gas. But in reality, we don't have only gas, but we also have a liquid incompressible system. And in a more common way, in a more general way, we have 2 or 3 phases. Okay, we have gas and oil, and we have gas, oil, and water. So we are progressing slightly. We understood the complexity and how the system behaves with a very simple case, which is gas, and then we're going to progress to something more realistic. Okay, and you'll see that things become a bit more complex. Okay, so first, yeah. So the comment about the network, just so you have some nice pictures. Networks. Production networks. Okay, and I put you a nice drawing, very simplistic. Okay. But then we can have, actually, I hope it ends up quite nice, because we have enough pictures that we can say how each element in this network looks like. So we have, for example, the processing facilities. In this case, we are using this Rubiales field in Colombia that I mentioned. Is producing viscous oil with a lot of gases, with a lot of water associated. And the processing facility looks like that. They had actually to damage a bit to make a clearing on the savanna to locate these facilities. Then if we go to the wells, the cluster looks like that. So I hope that's clear, but this is this element here. The cluster of wells, that's how it looks like. And we saw not only that the wells are there, but also you had a structure to commingle the production. Okay. That was able to test or to check, to be able to measure the flow rate of each well. And from there you had, I'm not sure, let me just put it big just to show you, just to refresh your memory. So after that, you commingle the production of all wells through a main pipeline that we call, in this case, we call it a flow line or a branch. Okay. And this is actually this flow line that goes here and then joins to a branch. Okay, that the branch is collecting the productions from a lot of clusters. So how that branch looks like? Okay, looks something like that. Okay, and that's actually exactly this point, and though that's also almost like a junction. Okay, what we were discussing last class. And if you see here, these metal plates, they are not really the pipe, but if we kind of try to zoom it in, okay, the pipe is actually under that. That's a metal plate that is just covering, it's just holding the insulation. Because this fluid, remember that it's heavy oil, so the viscosity plays a big role in the pressure drop in the pipe. So we want to keep, if the temperature is high, then the viscosity is low, and then the pressure drops will be also small. Okay, so we want to try to keep as much as possible this fluid hot. And of course, if there are some cows or there are some people that they go near to the pipe, if they touch it, they won't get any. Okay. And then we have, this other type of joint, and now you see that it's kind of bigger, and it's going to a main, and this is what we call the trunk line that appears on the figure. And also again, we have a junction. We have kind of a lot of junctions here. Okay, we can put it here. And that's actually this joining point. Okay, where the sub-trunk line or the branches, they join and merge through the main transportation pipe. And you can see that it's actually quite big. So really in our simplified drawing, when we say it's just a point, actually it has a lot of things, but you understand kind of the main principle. So that was one thing that we had pending. Out here I have a picture of the insulation, how it looks like. And there are different types, more expensive and less expensive. But basically you have the insulation layer, the insulation material. Okay, that is it's kind of shielding or trying to keep the heat losses to a minimum to avoid that the temperature will drop very much. And then you have, because this material is not resistant enough, it doesn't have enough, it's not consolidated enough, so you have a protection of metal on top of it. Now we go to the other thing that we had pending. We had kind of a lot of things pending today. And the other thing was, someone was asking how are all of these ICDs that I showed, okay, all of these meshes and all of these devices, how are they held together in the well, okay? So actually it's what we call the lower completion, and it's a pipe that, let me just take the picture down. Now I'm going to put comment. Okay, ICD, inflow control device, or ICV, inflow control valve, like we saw last class. And actually we mount them in a pipe, okay? The lower completion consists on a sequence of pipes that are just matched up together, and then every once in a while we put this with inflow control device, okay? And you see here something also that is interesting, that it has these things, these brown things in between. What are those? Yeah, packers. You have to speak louder with security. So these are packers that are actually to avoid, if you allow flow to go through the annular space, then actually you're avoiding in a way the purpose of the inflow control device, which is to control the flow. You want from this area to be producing certain rate, from this area to be producing certain rate. And if you allow annular flow, then the flow from this area could go here, okay, potential. So you put these packers, that they could be any type, but usually what we use, see here, also know that the casing, the upper casing goes up to this point, cemented, and from here we have just open hole, we have a naked hole, okay? So in that we run this pipe with all of these inflow control devices and these packers, and then we have to find a way to inflate. They could be either swellable or inflatable packers. By the way, do you take any course about completion that deals with completion from before? I know that there are some courses about drilling, deviated drilling. Do you see any completion in those courses? Yeah? Okay. So if you want more details, you can just go to these courses. Here we are only concerned about the kind of the flow aspects of the flow consequences that these devices cause. Okay, and usually that doesn't go all the way up, but you just hang it someplace in the casing. Okay, and for that you have to have a seal structure, which is a packer, and this packer is going to be in contact with the metal, and it's not going to be in contact with the formation, so it can be a bit more rigid. Okay, it could be a different type of packer. And you have here the slips, which are actually to hold it in place, and they're supporting in a way the weight of the structure. So I'm going to put you now a video, okay, because you were very interested in this autonomous inflow control device. So you can see, and also you can see there are some details about the completion.
North Sea has a 2,000 to 3,000 meter horizontal section.
Okay, the length of this section could be 1 kilometer, but now we are reaching length of 3 to 4 kilometers. That's something that is normal. And now you have to. Okay, so you see actually the same thing. It's a pipe match, and then you have each one in certain sections. You have a section here with a mesh, and and the packer. You see it here.
This means that if the AICV sees oil again, the valve will autonomously open and oil production continues in order to maximize recovery. The AICV is completely self-regulating and does not require any form of control, electronics, or connection to the surface. The AI...
Okay, and you see more or less the size. Actually, you don't have only one of these, but you have a bunch of them located radially to to take the whole flow of the well. And some people were asking, how does it work, or just out of curiosity. So just a very simple demonstration. We have done this here at the department, was to test. We had a problem. You had the same thing with anyone has worked before with mud pump? Yeah, mud pump or also cementing pump. These are positive displacement pumps that they have a chamber. Maybe we can make a drawing. Okay, I'm going to put the link here also later. Okay, the link of the video. So positive displacement pumps, they have actually is something like this. Okay, and you have a piston that is moving up and down. Okay, when it moves up, this valve opens. Sorry, when it moves out, when it moves up, this valve opens and fluid is coming inside the cavity, and then when it's going down, this valve closes and this one opens, and then the fluid is coming out of the cavity. So actually, we were just investigating the behavior of one of these valves that didn't open properly, and you have exactly the same issue. Here is on this autonomous inflow control device that you see. You have one part which is just a cylinder, and then you have a plate, okay? And then you have another plate which is movable, then can move up and down, okay? If you use certain flow rate, okay, nothing happens. But then if you use a slightly higher, okay, you see that it's attached, that these two plates are attached to each other, okay? So this has some kind of clinging effect. So it's calibrated, this device, when you have oil, that is just going to be separated between them. But when you have gas, actually you have less pressure drop, and then that's why they close. They touch and then it's closed. Okay, you have no more gas entering into the wellbore. So it's exactly the same principle. In these pumps we have if the valve has a lot of area, because in this valve you have to have a seal area. So if the seal area is very big, so you have this clinging effect, and the valve actually doesn't open when you are operating the pump. Okay, so that was one issue that was pending. I have another one. A lot of issues today. Oh yeah, the other one was the homework that some people. How many of you got negative NPV in assignment 2? Exercise set 2. How many of you got the 2 cases got negative NPV? So how do you explain that? Do you have any suggestion or any input? Huh?
Oil price.
Oil price? Might that be? But you know, in the original, this field, you see the name, right? This is kind of an acronym for which field? The Goliath field? Okay, that you got a presentation some weeks ago. And if you see the plan for development and operations of this field, the price they set it to $50 per barrel. So how, it's because we did something wrong, or they did something wrong, or we are smarter than them? Should we contact the oil company to see that,
But we use the Excel internal function, it gives positive value.
The internal function for what?
Yeah,
For?
MPV or MPV.
Okay.
Give a positive value.
But
If
very
not,
positive or slightly positive?
Very positive, 3 billion or something.
Okay, then there is something wrong with this Excel calculator. Okay, but the main explanation for that is just that it's a very small field first. Okay, the reserves are not very big, and it's kind of a marginal field. So really, all the economic value is all the time in between a paying project or a losing project. Okay, and of course you see it very strongly. If the oil price goes down, then you have already very quickly a negative NPV. But really, just to show you that the decision sometimes is not only related to the economic. The economic plays a big part of it, and is basically giving you the final decision. But sometimes there are also different things that you can think about before to develop a project. Like one thing that I wanted to bring to your attention is that the Barents Sea, where this field is located, okay, see here a picture. Okay, actually, the only 2 fields that are currently being produced, or just Goliath hasn't entered into production, but this is going to come soon. And you have Snøhvit, which we have talked a lot. Okay, but this is the only FPSO that we have in the area. So maybe these guys, what this company is thinking is about getting a position and a strategic position for future developments in the area. Okay, if they get an FPSO here, it's much closer than to send it, because the distance here is like 90 kilometers. So it's much to take all of these fields, the production, all of these satellites, they can be in a way tied into the production system, and then they have an advantage and kind of a strategical position. So even though the project maybe is not so valuable, they still get position, and for the future of the company in the Norwegian, the Norwegian Sea, it's important.
Also, when we were calculating the NPV, we were having negative cash flow. Like for example, you said that the life of the field is like 15 years. But how did you decide that this is 15 years?
This is from the plan for development and operations. All the information I took it from the plan of development and operations.
But the decision that how the life of the field, how do we decide it? So we see that when the cash flow is getting negative, we say okay, then at this time we will abandon this field. you don't go beyond the.
Yeah, it's usually you already have an idea. You have an idea what's the minimum, what I all the time talk, minimum operational rate. And if you are below that, then you just have to abandon the field. Okay. So usually you do it by the rate, and then with the economical calculations, you actually verify when are you going to have a negative cash flow.
Because when we were calculating it, so we were having like 5-6 years of negative cash flow,
Mm-hmm.
which was also causing more negative NPV.
Mm-hmm. Yep. But that's the way it was on the PDO. So that's also surprising, and we hope that someone from this INE company comes later. You know, they give some. You can write them if you want. You can, write them an email. We were doing this exercise with your data, and we got these values. Could you explain what have we done wrong? Of course, we have done a lot of simplifications. Okay, because you don't want to. If we wanted to cover all the details of the project, we will never finish. It's a work that is not suitable for one semester. But really, that gives you the idea that very simple calculations, you can still get a lot out of it. Okay, still have a lot of value.
One more thing.
Yes.
The OPEX, you kept it fixed for each year,
Mm-hmm.
but the oil rate was declining.
Yep.
Why?
Usually, it depends. Shouldn't be like that. Usually, the OPEX is. How many of you read the paper from Halderson? The economical interface. Only two. Okay, if you read that paper, you will get some indication. Okay, usually the OPEX, is going to reduce. It depends on the amount of fluid that you're processing. If the amount of fluid go down, then also the OPEX should go down. Okay, not only because of the processing part, but also maybe you're injecting some chemicals to avoid, wax deposition, and then every time you have to inject less and less chemicals.
So it depends upon the total produced fluid, not the
Mhm.
total oil rate.
It depends on the water produced, and the total gas, oil, and water produced. Okay. And of course, it should decline. Every time also you have less energy requirements, so the power generation has to be less, for example. Any other question? Yeah.
There was a question. How should we account for uncertainty of the project? I couldn't do that, maybe because of time. But how would you do that in an Excel spreadsheet? I was thinking about doing that according to problem 1. So we specified the maximum, minimum, for example, maximum oil price, maximum, minimum oil price. But the MPV calculation itself, it's not like one line of calculation. You have to go back and do
Yep.
it again. So how would you do it in an Excel spreadsheet?
Well, that's also another topic that we're going to cover later on. But really, the answer is if you want to consider uncertainty, you use probably Monte Carlo. Okay, you have to run a Monte Carlo simulation. You have to put for every price that you put, instead of a single value, you have to put it can be a range. It can be between a minimum and a maximum range. Then you give a distribution, can be triangular, uniform, whatever you want, okay? Whatever, the expert tells you. And then you have to run a Monte Carlo simulation using, the thing is that what you're saying is a bit difficult because every time you have to look, for example, maybe what you're saying is that you have to put all the data in the table and then you have to see how to run calculations automatically. You can set that up in Excel, but for that you have some other softwares which are doing for integrated asset modeling. Okay, that you're able to run multiple computations of some integrated model multiple times. Okay. But that was the right answer. You have to use some Monte Carlo simulation, or you can use also this decision tree to help you to calculate a total NPV of the project. Also, maybe we didn't talk much about the first exercise, but it tells you also that I think the distribution for the two engineers, they were slightly skewed, and one engineer gave kind of it was not very much. Okay, you see, if you think about in the practical terms, the engineer A just gave a slightly shifted to the right. Shifted to the right than reservoir B, but that gives you already, when you see the cumulative distribution function of the total recoverable reserves, that gives you already a big difference. Okay, and this is where I told you that the expert or the experience also of the engineer plays a big role in how to choose all the parameters in the distribution that you're using for your probabilistic calculations. Okay, So before we leave that, any questions? More questions about the exercise? So I really recommend if one of you has, the guts that if you want to write an email or maybe ask this person that came here, this Dr. Etemada, to ask about, more details about the project. Yes?
I have a question. I think these values are not correct. P10 and P90. They should be the other way around. Am I right? We have a 10% probability that we will have less reserves.
We will have more than that. Mm-hmm.
No, P10 should be this one, which is in front of P90.
It
Yes.
should be this.
P10 should be
This
this
one.
one. P90 should be this one, and
Yes.
P10 should be this one. Is it?
Yeah.
Okay. Yep. So we have someone that knows already that did something wrong.
And Professor,
Mhm.
how the curves change by the production? Probability curves?
By the production?
Yeah.
What do you mean
Time,
by?
By the time, as the production goes.
Well, every time it's like
Shifts to the right or?
these are done just at the beginning, just to take a decision if you're going to go for the project or not. But at the end, when you are producing your reservoir, you maybe realize that you didn't put a fault where there should be a fault, or that the reservoir is bigger than what you expected, or it does maybe smaller than what you expected. So you're reducing the uncertainty, but really you already took the decision. You're already kind of trapped with one system. You decided already if to go for it or not. Okay. But this is to allow you to take the decision if to go for that project or not. Yep. Any more questions? Yep.
Just to clarify, because I got confused. So the graph should be like this, right?
It doesn't matter how you plot it. The thing is what the number tells you. Okay.
Yeah. Because it means that we will have 100% probability that we'll have the maximum reserves.
Yeah, it should be other way.
Yeah.
It should be like that.
Yeah.
Okay.
This is what Michael Golan said in the class. that
Hmm?
Michael Golan, he said in the class that for petroleum reserves, this curve is always inverted.
We have to predict the data.
The thing is that you could also say that there is 10%, 100% probability that the reserves will be less than this number. Okay, so it depends on how you define this probability. Okay, so you have to, on top of the chart, if you want to use it like petroleum engineer is used to, it should be the opposite. But if you use it like that, then you should specify there is 100% probability that the reserves will be less than this value here. Okay, so it depends also on how you interpret the value. Okay, any more questions? No? Well, I just wanted also to let you know that I posted another exercise set, number 3. And that's due for next Thursday. And the idea is that you will be working in groups of 2. So it will be, I hope, slightly quicker. Still, if you do choose to do it individually, that's also possible. And the first problem is something that we have done in class, actually. Okay, but it's something more to explore. Those of you again who read the article by Halderson, okay, he states that the number of wells usually is selected by calculating the NPV for each solution or for each system with different numbers of wells. Okay, and then you choose the one that gives you the highest NPV. So that's what you're supposed to explore in this exercise. Okay, to change the number of wells, and then to see how the NPV is changing. But for that I have already done a lot of work, which is already we have the Excel sheet to do the economic calculations. So you just have to calculate the new production profile and put it in the Excel sheet. And also change, because the number of wells changes, so the drillix is changing. So that's the first exercise, and it's our nice field called here Attila, but it's actually Snow White. And the values that are in the economical calculations, they are, I think, accurate. Then the second exercise is about, again, what we have done for Snow White, but in this case, that you have to deal with a network. Okay, you have two templates, but now the templates, they are not symmetrical. But you can assume that every wheel in this template is going to behave the same way. So you can have one representative rate from that template, so you can analyze only one wheel bore. Then the flow line, you assume that is that rate multiplied by 3, and then you reach a junction, okay, which I call here the tau head. And then from the other template, and the two are producing from two different reservoir units. So the decline will be different in time according to dry material balance. Okay? And you have two pipelines, which that really doesn't cause any issue. The only thing is that you can analyze one and dividing the rate by 2. So really you don't have to pay. The only thing you have to divide by 2 the rate. So the thing is to calculate, to compute the production profile in time, and to also to compute the behavior of pressure in the most important points in the system. That means at the bottom hole, at the wellhead, at the template, at the tau head, with time, and see how they evolve with time. And first you will be operating in plateau mode, and then you will be operating just in depletion. Okay? And we might, if you need, I recommend you start working on the exercise, and if you need, we might have some session maybe tomorrow or next week if you need some clarification. But I recommend you really to start working on that, because you need some thinking. If you told me that you understood everything on networks, so now I will see if it's correct or not. Okay. Yeah. So they are producing, and that's actually from a real field. That's Gulfax, that they were producing actually from the oil layer, and after that, when the oil layer was depleted, they start to produce. They change the well from an oil well to a gas well. Okay, so they recomplete it in an upper section. And then the last problem is there is allocation that we are going to talk today, but you really don't need allocation for that. That is actually, you have a system, you have a downhole network of three layers producing through the same well, and you have to calculate how much is coming from each layer, because each layer has different partnership. Okay, and I think it's indicated here, all the companies. Okay, layer name, they are like that, and companies, so each company has a different percentage of ownership in each layer. So you want to calculate how much is coming from each layer, and then how much of that rate belongs to which company. And for that you have to, it's slightly challenging, so you have to think challenging in the way to solve the network. Okay, how are you going to set up your Excel sheet the best way possible to solve the rates? Any question? No? Okay, so let's finally start with the topic for today, that is allocation. So this is a comment. Yeah. Comment on exercise 2. Okay, that not only the decision is not always based on NPV. Sometimes the field really is, if there is any slight change, it will be a marginal, it will have a marginal payoff, but sometimes it's about a strategic positioning. See if I forgot to put some other nice pictures. No, that's what's coming. Okay. So allocation. Okay. Allocation is basically to determine from the main flow rate that you're getting, from the main oil flow rate and gas flow rate and water flow rate, where is it coming from? To determine where or in a way it will be to partition okay, and that means you might say it's coming if you have, for example, two reservoir units, like in the case that we are discussing here. Okay, you have, let's say, two wells, and then they join and they merge, and you have another reservoir unit. Okay, and you have here the total field production, Q oil, Q gas, and Q water. It's not only to know from which reservoir is it coming, but also you want to know from which well is it coming, and if one well is completed in different formations, also from which formation is it coming, right? So we can say where are the rates coming from, and this refers to reservoir, this refers to well, this refers to formation. Okay, we have to know exactly full control. If we get 1 barrel, how much of this barrel, 30% is coming from where? Okay, and so I already told you, already give you kind of a spoiler. Where are we getting this information? What do we need to get that? Okay, anybody remembers from another class?
Flow meters.
Flow meters. Okay, we get that information flow meters. So the first, here in the North Sea, what kind of system is typical that we use for subsea wells? Huh? Multi-phase meter, but before that we have 2 lines. Okay, one test and one. So one option is to have test separator. That actually we had the wells. You can put here well. Again, we have a on-off valve, and we had 2 manifolds. Actually 2 lines. And remember, this structure was very important for what? Why people use this structure? Pigging. Okay. So if you want to, here you have the main separator and you have the test, and just simply if you want to put any well to the test, this one is closed, this one is open, and this one is open, and this one is closed. Okay, so you just open with the combination of valves, you route the production of that fluid to a test separator, and like that you measure how much is that well producing. Then you had another option. What do we do in landfills?
You have separate.
We have portable separator. Okay. Okay. So, and that's basically, of course, we cannot have something like that for subsea. It will be too expensive to mobilize a vessel every time we want to do a test. But for landfills, we use portable separators. And yeah, I think I had some other picture here. And that's already when it's on the floor. This is when it's being transported on the truck. This is when it's on the floor. Or the other option, if we want to avoid the 2 lines and we cannot do test separator, we use a multi-phase flow meter. But flow meters, the thing is, all of these things have issues. Okay, we cannot trust 100% on the measure of these measuring methods. But really, there was a lot of this mistrust on the use of these multi-phase meters until recently. Okay, the technology has improved quite a lot, and people now are trusting, and actually, because it's a very big. So why do we do allocation? Why do you think? What is the main reason to do allocation? For the money, okay? We want to see how much we have to pay to all of our partners, okay? And really, you don't want to have something that is not, you don't trust so much to split the money, okay? It's like you go to a very well-recognized bank and you go and leave them the money, okay? Or if you go to, I don't know, to a small shop that is kind of hidden in the center of town and they open one day and one day they don't open. You don't want to leave your money there, okay? You don't want to trust these guys. So in a way, it's like that. People didn't trust very much on multi-phase meters until recently. They have really shown that the technology works, but you have to do calibration. That means that every once in a while you have to use either a test separator or something to calibrate this equipment. Either you have to take it, if you have it subsea, retrieve it and test it onshore and then bring it back. Or if you are in land, then you have to use a test separator to verify that you're getting the two values are the same. And if not, you have to kind of use some tuning. Okay, so yeah, let me just paste. I don't want, just for your sake, so you have it for when you're reading the notes. Here there are some, actually I think they're taken from Wikipedia, to what is allocation, but it's exactly what I told you. But there is really a very big issue with allocation. That is that, what do you think might be an issue with allocation? What problem? Okay, I trust, I have these meters, I know how much is each well producing. What is the main problem? Okay, that the values don't match. Okay, when I do the measurement in each individual well, I say I should get 10,000 barrels, and then you go to the facility and actually you're getting 8,000 barrels. You get a mismatch. So really allocation is a way, it's also to determine where each fluid is coming from, but also to reconcile the value that you have measured, or that actually you have in the tanker, that is actually you physically can measure, you know already that is there, and the value that you're measuring with the meter. So reconcile, and that I think is mentioned here. Of the meters, okay, with what I actually have at the end of the day, what I actually measure in the export facilities, in the tanker, in the storage. I think it's okay if we, take a break now and let's say 10 minutes, and then we come back with the second part.